So let's prove the following claim. We'll call it a day. Claim for all n greater than or equal to 0, the sum from k equals 0 to n of k is going to equal n and then plus 1 over 2. That's the weird claim. And if we just do an aside and kind of check it out a little bit, if we do the sum from 0 to 0, okay, well, that's just 0. And if we look at 0 times 0 plus 1 over 2, 0 checks out. If we look at the sum from 1 or from 0 to 1 of k, well, that's 0 plus 1, which just equals 1. And then 1 times 1 plus 1 over 2, that's 1 times 2 over 2, which equals 1. Checks out again. The sum from k equals 0 to 2 of k is 0 plus 1 plus 2, which of course equals 3. And then if we do 2 times 2 plus 1 over 2, we get 2 times 3 over 2. The 2's cancel, we get 3. Oh, checks out. Do one more. If we do k equals 0 to 3 of k, that gets us 0 plus 1 plus 2 plus 3. 1 plus 2 is 3, plus 3 is 6. And if we do 3 times 3 plus 1 over 2, we get 3 times 4 over 2, which is 12 over 2, which is 6. A very nice formula. Very nice. It all works out. And the story goes, well, this is discovered by a little Gauss. Gauss is a mathematician. He was in grade school. And his teacher, because he was being a little bit, he was being a smart ass, let's be honest. He was really smart and he was being an ass about it. And his teacher put him in timeout and said, okay, you can get out of timeout as soon as you add all the numbers together from 1 to 100, right? And, you know, she was an elementary school teacher, like, you know, she didn't know advanced math. No one did at the time, really. Gauss was making it up. And she thought this would take him forever. But Gauss started to look at it and he went, okay, well, wait a minute. If I do 1 plus 2 plus 3 plus 4 all the way out to 96 plus 97 plus 98 plus 99 plus 100, think about this. If I put the 1 and the 100 together first, because remember, you can add things in any order, that's fine. Gauss knew the commutative property. I get 101. So let me group 100 and plus 1 together. Then you said, oh, wait a minute. I'll draw it like this instead. Let me also group 2 and 99 together. And you also said, wait a minute, let me group 3 and 98 together. And then we also group 4 and 97 together. And he kept going like this. And you noticed, what's 100 plus 1? Well, that's 101. What's 2 plus 99? That's 101. What's 3 plus 98? That's 101. What's 4 plus 97? That's 101. If you group them together like this going in, you keep this 101 in the grouping. That's the same for all of these. So all you need to know to add them together, I'm getting really excited about this. All you need to know to add them together is how many of these groupings are you going to have? Well, what do you guys think? How many of these groupings are you going to have? Like where do you meet in the middle is really the question.
N over 2 groupings.
And there's going to be N over 2 groupings, right? So this is going to be, so it's going to get all the way down to, I think it's eventually going to get to, what, 50 and 51 or something like that? Yeah. Right, so you're going to get to this, but you're going to have 100 over 2 of these. So the final answer is 101 times 100 over 2, which you can do out. But the point is, this is like n plus 1 times n over 2. Brilliant, 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 brilliant little boy. That's the story. But we're going to prove it in a totally different way. but that's how he did it. So proof, we're going to say proof by weak induction on end. You always start with your base case. And for your base case, right, you want to prove for the first one. Since it works for all n greater than or equal to 0, you want to start at 0. So I'll say, want to show this right here is going to be like our P of n. Want to show P of 0, i.e. the summation from k equals 0 to 0 of k equals 0 times 0 plus 1 over 0. Because you plug 0 in for n, that's what you get. That's what this predicate's saying. So I'll say let n equals 0. And the summation from k equals 0 to n of k is the same thing as the sum from 0 to 0 of k, which just equals 0. Further, n times n plus 1 over 2, in this case be 0 times 0 plus 1 over 2. Anything times 0 is 0, right? So this is just 0. Thus, the summation for k equals 0 to n of k equals n times n plus 1 over 2. So the base case holds. Does that make sense? We just showed it works for 0 in very formal mathematical language. Inductive step. Here's the interesting one. Remember, here we want to show that for all n greater than or equal to 0, we want to start at 0, otherwise there's a gap in our chain, it's no good. We want to start at wherever the base case was. For all n greater than or equal to 0, because the base case starts us off, P of n implies P of n plus 1, i.e. in this case, that for all n greater than or equal to 0, if the sum from k equals 0 to n of k equals n times n plus 1 over 2, then, so if it works for n, we want it to work for n plus 1. Let's be very careful with what the statement for n plus 1 is. Say for n plus 1, it's in the summation from k equals 0 to n plus 1 of k. If you add one more number on, that should equal what? So if this predicate, like what is P of n plus 1 is the question, right? It's saying that the summation of k equals 0, we just plug an n plus 1 in for n, of n plus 1 of k equals, so what should we plug in here?
n plus 1, n plus 2.
Exactly, n plus 1, n plus 2. Because that's what this is saying for n plus 1. Like if it holds for n plus 1, we get an n plus 1 for n, and an n plus 1 here, which is n plus 2. So I'll actually write all that out. So we get n plus 1 here, and then we get n plus 1 here, which is n plus 1 times n plus 2 over 2. If we can show this, we can show that this statement holding for n implies it holds for n plus 1, and that's the chain, that's the link, and we can make our chain reaction. So like I said last time, this is its own mini proof to prove this inductive step. And again, I'm going to prove it by direct proof. So I'm going to say, let n be any integer greater than or equal to 0. Then, yes. And I'll say assume. So now we're direct proof, right? We're proving an if then, which we're doing here. You first let n be in your domain, and then you assume the hypothesis. So we're going to assume this part right here. So assume it holds for, assume P of n holds. We're going to prove P of n plus 1 holds. So assume the sum from k equals 0 to n of k equals n times n plus 1 over 2. Under this assumption, we want to show that P of n plus 1 will hold. So I'll just say, consider the next sum. And remember, we want to show that this equals n plus 1 times n plus 2 over 2. So consider this next sum. The sum from k equals 0 to n plus 1 of k. So remember, I said the key to all induction stuff, right? All this induction crap, it's not crap, it's beautiful, is to try to get P of n to help you prove P of n plus 1. And the way you do that is you kind of want to get P of n to fall out. Like last time when we manipulated our 2 to the 2n plus 1 minus 1, we eventually got a 2 to the 2n minus 1 to fall out. And then we could use things we knew about that to prove things about the n plus 1 case. So how can we get maybe just this to fall out? From this.
Separated into two separate, or yeah, into two separate summations.
This is called peeling off the last term. So note that this is the sum of everything from 0 to n plus 1. But that's the same thing as doing the sum of everything from 0 to n, and then adding on n plus 1. Right? This is by peeling off the last term. And you can always do this. I hope this makes sense. Right? I mean, all we're saying here is that this right here is like 1 plus 2 plus 3 all the way out to plus n plus 1. And we're just saying, oh, that's the same thing as doing 1 plus 2 plus 3 all the way out to n, doing this sum first, and then adding an n plus 1 on top. Right, same exact thing. But that helps us because we know something about this. What do we know about this sum right here?
The first half of it already follows because it's part of our assumption.
Yeah, we're assuming it follows. We're trying to show if it follows, the next one will follow. Because once we have that if, then that's the link in our chain. So assuming this is true, this is going to be n times n plus 1 over 2 plus n plus 1 by our assumption. This one right here. So assuming this is true, we get this. But then everything falls. Because then we get n times n plus 1 over 2 plus 2 times n plus 1 over 2 by getting common denominators. And then this part equals n times n plus 1 plus 2 n plus 1 over 2 by fractional addition. And we are so dang close. I'm going to finish off the paper again. then this equals, well, I can factor the n plus 1. By factoring but then we have it. That's what we wanted to show. This means that if this formula is true for 0 to n, the formula will also hold from 0 to n plus 1. That's the link in our chain. That's the inductive step. So that brings us to the conclusion. Therefore, for all n greater than or equal to 0, the summation from k equals 0 to n of k equals n times n plus 1. So Gauss's way was pretty elegant, but it had dots in it and things like that. It kind of had weird little places that weren't exactly rigorous and were kind of wrong. This is a totally rigorous, formal way to prove this is true. And I hope it makes sense. We proved it works in the base case, it works for 0. And this inductive step shows if it works for n, it works for n plus 1. Just since it works for 0, it works for 1. Since it works for 1, it works for 2. Because it works for 2, it works for 3, for 3, for 4, for 4, for 5, for 5, for 6, on and on and on and on like that. Does this make sense or am I going crazy? Well, I guess those are the only two options that kind of put you guys in a precarious spot. You have to call your instructor crazy or you have to say it makes sense.
Maybe both.
Yeah, you might be going crazy.
Does that mean it's not making sense, or are you just busting my balls?
Yeah, it makes sense.
Cool. So that's class. I went over. I went way over. Sorry about that, guys. But I was probably gonna spend so much time explaining Gauss. I couldn't not. It's my weakness. But anyway, I don't want to take any more of your time. So thank you guys for coming to class. Any questions?